Moving forward with our networking module, and today's part is probably most important as part of the networking module, where we're going to be talking about extensively about routing tables. And the reason it's kind of one of the most important part, because it's basically combines two key features of the networking layer protocol: control plane and the data plane. And to give you a basic idea, so the routing table is the element that the control plane uses to inform the data plane how the decision should be made when the packet arrives. And the data plane uses this routing table to simply obey the decision of the control plane. It just depending on from which perspective you're looking at. And basically, on a high level, the packet arrives within the data plane. Data plane looks up in the routing table that contains multiple entries, or hopefully multiple entries. You find out which entry is supposed to be used in this specific case, and we're going to be talking about how exactly this matching process is happening. And looking into this specific entry that indicates how this packet needs to be forwarded further. Either it needs to be just directly put on the link, or it needs to be handed over to a specific gateway. The granularity of the routing table is not necessarily individual IP address, but rather a whole subnets, like the ones that we were talking about in previous part. And basically, it can contain one or more prefixes that has like /22, /25, /16, and whatever, different slashes. And we're going to be talking more of the exact content of the routing table. This is an example of the routing table content, and to highlight, at the very least, this routing table is basically a list of entries. Like in more complex cases, it's something like a Patricia tree, or potentially even more complex structure to improve the performance of the looking up. But at the very least, each entry in the routing table, logical or physical entry in the routing table, contains the network address. That's including the subnet ID or network mask. It's basically the same thing, and in an example I'm giving you both. It may contain a gateway. So this one has different notations in different operating systems, in different literature. What I'm showing here is basically a designation. It's either some host in this network is available directly in this subnetwork, like if you just can put this IP address or a packet destined to any IP address to this network directly on a link, and hopefully someone will receive this packet, or it can be reached via the gateway. This will be additional conversation we're going to have as part of the link layer module, but just remember, as part of this conversation, in order to send packets to a specific subnetwork that identified via the specific gateway, you have to give this packet to the gateway. And notably, the gateway IP address needs to have a corresponding entry in the routing table that corresponds to via direct entry, like in some form. Just in case in a Linux operating system, this via direct is indicated by like 000, but it's nothing really special about that. And in addition to this basic information, it can also include the interface information, like to which actual interface this packet needs to be forwarded, and can include additional flags like metrics, like some additional routing flags, and so forth and so on. And the routing table exists basically on all systems. It's not only the routers that have routing tables, but rather even the same host, and even the host in kind of this iPad, this iPhone, even the camera that I'm recording, they all have some form of a routing table. It may be quite simple, but it can be also quite complicated. And I give you examples of Linux routing table and Mac OS routing table. And you can easily get routing table from the Windows machine. It's just a slightly different variation of this command, or maybe a slightly different command. And as already highlighted, the content, the critical content is the subnetwork. In this case, it's called the destination. It's net mask. It's kind of correlates to the destination. Again, in Linux, it's written as a net mask, and as part of the Mac operating system, they use simple /32 or some other slashes. And there's also gateway that I already indicated. In some cases it's specified as zeros, and on Mac it's a little bit finicky that how they designate the different gateways or different information. What else I would like to note here, as on the previous slide, so there's one entry that marked out as a default route. So this one is a little bit special. So logically it's not really special, it's just an entry that has a network address of 000 and a subnetwork mask of 000, but it just happened to be to cover a complete range of IP addresses. So basically, if you remember how to calculate the ranges, for this network address 000 and subnet ID 0, the range is from 000 until to 255, 255, 255, 255. And the basic role of this entry is to capture anything that was not captured before. And in that case, you simply try to obey the decision of this default route entry. You don't have to have the default route. It's just most cases in systems that connected to the internet, like host systems that connected to the internet, you would have this default entry. Routers in the middle of the internet, they don't have the default entries, and some of the systems that are not connected to the internet or not yet connected to the internet, they also will not have a default route. Okay, so now talking about how you get the routing table. And as I highlighted on this slide, the routing table can come from several sources, and just let's try to go over one by one. So first of all, you will get some of the routing entries automatically. And this automatic creation of entries is via configuration of the interface. So remember, from the previous part, I was talking that each interface have to have at least one IP address and network mask associated in order to start communicating using IP protocol. And to do so, you have to configure those things. As soon as you configure IP address and network mask, this automatically creates an entry. So for example, I gave you kind of very silly example of a 3 hosts network with 2 subnetworks. And what you see, there's a PC1, router 1, and router 2. In PC1, as soon as we configure this 201.10.7.42 IP address with whatever network mask, we immediately creating the route table entry saying that all IP addresses within this range, and I hope you can calculate the range, can be reached directly over this Ethernet ETH0. That's it. That's all what being said by the creating the entry, by just configuring the interface and automatically creating the entry. Similarly, the same thing happens on the router 1, but just because we configure 2 interfaces, we're going to have 2 routing entries automatically created. And finally, on router 2, potentially this router 2 will have more interfaces configured, but on this picture, there's just only one, just some kind of ETH15 that been configured with this specific IP address, this specific network mask, which automatically creates this entry. That's it. So this kind of, just remember, there is this automatic creation of entries in a routing table. And if I ask any questions on some maybe homeworks, maybe exams, you should have a very good understanding of this process. Okay, so then there's the second part. The second part is a little bit complicated, a little bit more complicated. You may need to have explicit routes set up. So for example, in router 2, in order to reach the PC1, so like in the configuration that we have so far, it actually doesn't know how to reach it, because the only host that the router 2 can reach is router 1, because it has a routing entry and it can reach any IP addresses on that specific subnetwork. And 201.10.7.42 doesn't fall within whatever range of 126, 255, 103, and whatever afterwards. So basically it doesn't match. And there are several ways how you can match it, and one of the ways is to have explicit kind of route pointing to somewhere else. It's an explicit route that covers that IP address and specifying how to forward that specific packet. And I gave you already an answer on the slide. which simply means that router 2 can configure this specific entry 201.10.6.0/23 that needs to be reached via 126.255.103.42. So that would be the routing entry that you can create either explicitly manually, or it can be created automatically if we're running some form of routing protocols, and that will be subject of a separate part in this module. So that configuration of router 2. But there are two more routes that most likely would exist in this environment, one on the host and one on the router 1. So on a host, you most likely want to, if you hopefully connected to the internet through the router 2, then you may want to forward all packets through the gateway. So basically, if you have a home gateway, you need to have this automatic route that basically saying, oh, I can reach the gateway directly, but then you want to have a route saying, oh, for any other IP addresses that I cannot reach directly, I want to forward them through the gateway. So that's basically the notion of the default route. And something similar can happen with router 1, where it has a designation of all packets that it doesn't know about except one. So for all packets that it cannot reach directly, meaning it's not within the range of 126.255.103 and whatever afterwards, or within other range of 201.10.6 and whatever until 7.254, then you can also create the default route like 000/0 and specify that this router will need to go through 126.255.103.15 in order to kind of deliver this packet successfully somewhere else. So I think this captures quite a bit of notion of automatically created routes and explicit routes and their purpose. So that's kind of the basic idea. So far I was talking about the routing table in general, meaning when I'm there's some entries in the routing table and I'm trying to match one of those entries. But there is a little bit additional logic associated with the routing entry because, for example, in the same routing table, there are potentially multiple entries that can match the same IP address. For example, if I got IP packet with destination address this 201.10.7.15, this packet, if I try to decide where to forward, will effectively match ranges defined by the entry 2, 3, and 5. And I hope you can calculate and know how to calculate those things. You need somehow, for the computers, you always have to have some logic to define what to do if you have multiple choices. In networking, in IP networking, it has been very clearly defined. You have to pick the longest prefix, meaning you have to pick an address with the most bits designated to the network ID. So for example, you will pick 24/8, or you pick /16/0, and so forth. And in this specific case, I hope you can easily answer the question among the three entries that are matched to this IP address. You will see that the only entry that will be actually picked will be entry 2, because it has the longest prefix. I mean, the subnetwork ID is basically the biggest number. I hope you got a very good idea that of the longest prefix match process. What I want to do next is just a little bit give you a few tricks of how to exactly match entries without actually calculating any ranges, because the process is quite simple if you know a little bit of binary arithmetics. So basically what we can do, instead of getting a network address, subnetwork mask, calculating the ranges, and then looking whether the IP address is within the range or not within the range, you can simply do a little bit of tricks with the network mask and destination IP address and network address in the routing entry. And I gave you a few examples already on the slide. So what you can do is simply take the IP address that you got, the 715, and get the entry. Like for example, we're looking at the entry number 1 and getting the subnetwork mask from that entry. And what we do, we're trying to get the IP address, a binary AND with the subnetwork ID and get some result. So for example, in the first case for the entry 1, we're gonna get 201.10.7.0. And the kind of condition whether it matches or doesn't match is simply if the network address in the entry equals to whatever you calculated right away, like with this binary AND operation, then it is a match. In this specific case, it's not a match, so it will be rejected, like it's not even a candidate to be considered, and then we're moving forward. So for the network, for the entry 2, we do exactly the same operation, but we're just picking different subnetwork ID, subnetwork mask. And in this case, it's 715. We end it binary AND with a 255, 255, 2540 because it corresponds to /23. And in this case, I hope you know how you get to this point. You will get the 201 1060. How I got it, and I hope you can prove me if I'm wrong. You can clarify this. And so this is a match. Technically, you still need to go later. In this specific case, like because I ordered entries by the size of the subnetwork, we actually can stop looking any further as soon as we got the match. But let's imagine the case when the order wasn't it wasn't pre-sorted for us, and it was just a plain list of entries. In this case, we still have to continue matching and just remembering all the matches that we had so far. So, for example, we can look at the entry 3 and figure out that it's also matched and our IP address, and kind of look at the entry 4 and discover that it doesn't match, because if you take it 201 10 7 15 and do binary AND with the 255000, you will get the 201000, and which doesn't match 4000. And finally, you can match anything with a default route because simply any number and binary AND with 0 will get 0, and which is matches 0, obviously. And again, in a hypothetical case, if we had this entry is not sorted, you just have to lay down all the matches. So you have a match if we're entry 2 with the length of 23, you have match of 3 with a length of 21, and you have match of 5 with a length of 0. Then you simply pick the longest one. So you pick the entry 2 as the match. And for the fun of it is exactly the same operation. I just gave you a few examples in a little bit more animation. So if you want to do it manually at home. To give you small ideas about the kind of the process. So the process I described is the logical process that routers can do. So for example, they can, when they construct in tables, they can simply order them by the length of the subnetwork, and every time they receive a packet, they simply go one by one in this routing table. But if you remember how many prefixes the routers deal with from the previous part, then you probably realize that it cannot be really done at that scale. If you want to kind of forward the packets, and we only have like a few nanoseconds to spend to process the packet in the first place. So people actually designed a few more complex data structures, like a Patricia tree, like binary Patricia tree, less key area Patricia tree when we're like looking up a little bit more stuff. And there are actually a number of special hardware that is available to actually speed up the process of looking up. So instead of just doing one by one, the process you can kind of look up extremely fast. And today's router, they don't, I mean, the big routers, I'm not talking software routers. So those guys spend like, I wouldn't say less than 1 nanosecond, but on order of a few nanoseconds per packet to figure out what entry matches the incoming packet. Okay, I hope it was quite interesting, but I understand it's a little bit heavy to remember, but you have to have very good understanding of what is routing table, what the content of routing table is, what entries are, like how they look like, how they're being added to the routing table, like what's kind of actual meaning of the routing table entry. And especially you need to have a very good understanding about how to match a packet to the routing table and how to make a decision, like using, for example, longest prefix match. And kind of to capture all those stuff a little bit more in detail, this is exactly the reason for our project 3, where you will have to implement basically the routing table decision. Like you'll need to implement a little bit more than that, but you will have to really deal with a decision of how to kind of, given the IP packet, given this destination IP address, how to look up the routing table. Okay, so it was a little bit intensive, but that's it for this part, and see you next time.